Very good evening, everyone. Welcome to the Saturday series. Today's topic is about supercapacitor, future of energy storage. Today's session will enlighten us on the role of supercapacitors in the energy storage industry. Also, flexible energy storage research work happening in Amrita Biosensor Research Lab and many other points. Well, today we have a faculty from Amrita Vishwa Vidyapeetham, Dr. P.V. Suneesh. He is the Assistant Professor of Department of Sciences, Amrita Vishwa Vidyapeetham, Coimbatore. So he will enlighten us on the wisdom of supercapacitors. So before getting into the section, if any of the participants have queries, please type it in the chat box. Suneesh sir, I welcome you to the session. Therefore, we can start the series. Over to you, sir. Thank you.
Thank you. Thank you very much. So today, good evening to all of you who are present here. And we are going to discuss on the energy storage devices. And all of you know that these energy storage devices, at present, you may be attending the session from a mobile phone or a laptop. And all these devices are running with batteries. And these, so is it in the presentation mode?
Sir, it's in the presentation mode, sir.
Yeah. So all these devices are working with energy, which is actually given by the batteries, which is there we are using. So we are going to discuss one of the important energy storage device, which is coming into the market, and some of the devices are there in the market with supercapacitors as the energy storage device. And these devices, all of us know about capacitors, and capacitors are known to us for very long time, and batteries, which are also known to us for very long time. And these supercapacitors are actually a bridge between the conventional secondary batteries and the conventional capacitors. So let's see what are all these devices are, the energy storage devices, one by one. I'll try to explain the science of working of these devices also. So if you get any queries, you can put it in the chat box at the end. I'll be happy to answer for those questions. So I'm working in Biosensor Research Lab, Department of Sciences, which is situated at Amrita Vishwa Vidyapeetham Coimbatore campus. We are working on the electrochemical devices, both on the energy storage devices and also on the electrochemical sensors. So we know about electrochemical energy devices, and this image will be familiar to all the people, those who are attending here. This is an image of Daniel cell. And we know it's working as zinc as the one of the electrode and copper as the other electrode. We will get power from this device. That's the electrons which is flowing through the external wire. And if you are connecting a load, which is the device like laptop or mobile phone that we are connecting there, or a bulb which is connecting there, and that will actually, if it is a bulb, that will glow. And I wish to show this image because I want to tell you how these devices are working, and then how it can be transformed to a practical device which we can use in our day-to-day life. So this is the science here. Zinc, which is getting zinc, the metal that we are using we are dipping into an electrolyte, and I can say that zinc, which is a electronic conductor, that is dipped in an ionic conducting medium of zinc sulfate. When we are dipping so, zinc will get when we are connecting that with another electrode, which is a copper electrode, where copper is dipped in copper sulfate solution. Again, that is a electronic conductor, which is dipped in an ionic conductor. Then when we couple them, there arises a potential difference between these two electrodes. Potential difference means it's the tendency to undergo some reactions. A potential of an electrode means, say, zinc, which is having higher oxidation potential, means this is having more tendency to get oxidized. And copper, which is having less oxidation tendency when compared with zinc, and thereby which is having higher reduction potential. So copper is having higher reduction potential. So when we connect an electrode of higher oxidation potential with an electrode of higher reduction potential, there is a potential difference. That means there is a reactivity difference. And that leads to energy generation. That is what is happening here. Zinc, which is having higher oxidation potential, that means oxidation tendency, that will get oxidized to zinc 2+. And on the other side, copper having a reduction tendency. So copper 2+ ions will get reduced on the copper electrode, and zinc electrode get oxidized. Those electrons will move through the external circuit, and that is coming to the copper surface, and copper ions are getting reduced. So this is the chemical reaction that is happening there. And from that, we are getting the electrons as the output. And in between, you can see sodium ions and sulfate ions, which is kept in a tube kind of structure that is acting as the salt. So this device is a conventional benchtop device, but how we can transform that to commercial prototype, that is the one that you are seeing on the right hand side. You are seeing the image or the anatomy of the Duracell or the AAA and AA batteries that you are seeing in the market, where you have an anodic material and a cathodic material. You can see that one here. And then so there is an anodic material and you have a cathodic material. So here in the first image, you have two beakers in which these electrodes are dipped. But here you can see this is the anodic material and the middle one is the cathodic material. Electrolyte is incorporated in between this. And we know that if these two electrodes are in contact, they will get shortened. And in order to avoid that, this electrolyte will be incorporated in a cloth material, which is non-conducting in nature. And then we will be assembling that one and in the form of a cylinder, and we can get the cylindrical battery, which is available in the market. And from the cathode, we will take an electrical connection or a terminal will be here. And in the anodic side also, we will connect that one to a bottom metallic plate using the metallic connection we will make in the form of a nail. And then the bottom part you will see as the anodic part and the top one is the cathode. And that's why in the batteries, if you check, you can see the bottom one will be the negative terminal and the top one will be the positive terminal. And when we connect these two, and if we incorporate load in the circuit, the battery will start working, and the load, if it is a bulb, that will flow. And what is the potential difference which will get created here? And that potential will be the battery potential, and which is named as open circuit potential. But when we connect a load, slight drop in that open circuit potential will happen, and the current will flow through that and flow through the device that we connected, and we will get the device working. And we have these devices, this simple principle that is applied, and various devices are there in the market. So in all these devices. The first one you know, which is batteries. And we know that batteries are of two types, the primary battery and the secondary battery. In all these batteries, there will be two electrodes and an electrolyte in between. And the reaction happens when they are in when the anode is connected externally via wire to the cathode, and the energy supply happens. So the first one, which is shown here, is the batteries, and these the Duracells that I have shown here, they are actually primary batteries, and there are secondary batteries. So this one you can see the lithium battery, which you normally use in your laptops, and the square kind of this battery you can see, that is the battery that you are using in your laptop. They are actually the secondary batteries which can be recharged. Then the second image that you are seeing here is another electrochemical device, which is a dye-sensitized solar cell, where again you have two electrodes. Here the titanium dioxide, which is coated with a dye, act as the electrode, and on the other side you have the platinum coated carbon electrode as the second electrode, and you are having an electrolyte in between that, which is an iodide based electrolyte. And when the light falls on this system, the dye absorbs the light energy and transfers the energy to the titanium dioxide filling here electrode. Because titanium dioxide as such, it cannot absorb the light energy from the sun, and thereby we will this dye will help in absorbing that light, and that gives the energy to the titanium dioxide filling. And this process is known as photosensitization. And when the electrolyte is in contact, and these electrode materials are also connected via external wire, and light is supplied, the electrochemical reaction happens, electrons are generated, and that electrons will move through the external wire. You will get the power outcome. That is the second type of electrochemical energy storage device that I want to show. And the third type of electrochemical energy storage device shown here is a fuel cell, where a fuel, here it is shown as hydrogen, that is burned or that is oxidized using oxygen on electrode surface. And when this reaction, hydrogen and oxygen, combines in an outside environment, that will lead to the thermal energy. But here, when this reaction is happening on an electrode, then we will get electrons out, and that electrons can be sent through the external wire, and we will get the power out. The potential of these batteries again dependent on the cathode and the anode materials used, and also dependent on the electrolyte used. Then the fourth one that you are seeing here is the one that we are going to discuss, which is electrochemical capacitors or supercapacitors, or it is otherwise known as ultra capacitors. Okay, let's see what this device is. So before discussing the science of supercapacitor working, we will just compare the different devices which is available, and what are their advantages, what are their disadvantages, and why some device is better over the other, that we will discuss. So the plot that you are seeing on the screen now is known as Ragone plot, where on the x-axis you're seeing the power density, and the y-axis, which is energy density. So don't fear with these terms, but this energy, we know that energy is equal to V into Q, voltage multiplied with the charge stored there. And power, we know that V into Q by T, or VI. So from that term itself, we can easily understand these x and y axis terms. Energy means more charge stored. Energy, if it is increasing, energy density, if it is increasing, then it tells that the charge stored in that device is more. And then power density increases, that means it is delivering the charge quickly, or it is having high current. It can deliver high current, probably for shorter time. And thereby we can actually group, differentiate different kinds of energy storage devices. And we can see that you all might have seen the capacitors, and the capacitors charges quickly. We can charge the capacitors quickly, and it discharges also quickly. The charge which is stored in that device, it will discharge within seconds or milliseconds. And then fuel cells or batteries, they can store more charge, but those batteries will deliver low power or low current for a higher duration of time. And thereby, fuel cells or lithium battery or the NiCad, nickel cadmium battery, or lead acid battery that I have shown here, all these devices are having higher energy storage capacity, but they are having lower power storage, power delivery. So these supercapacitors are coming in between that. They have moderate energy storage density, and it has high power density, which is close to the capacitors. And there are a lot of research which is happening there in order to improve the storage capacities. And that's why we are taking this topic today for the discussion as an emerging technology for energy storage. Now, any electrochemical energy storage device, if you want to see its performance, we have to think of these four terms, basically. One is the voltage. So we know that when your mobile phone that uses a lithium battery, that lithium battery can provide a voltage of 3 volts, 3 to 3.4 volt voltage it can provide. And that is actually dependent on the electrode material that we are using inside. So the electrode material in this rechargeable battery in your mobile phone, the lithium intercalated carbon electrodes is used as the anodic material, and on the cathodic side, cobalt or nickel oxide, in which lithium intercalated, is used as the cathodic material. And the electrolyte, which is a aprotic organic solvent, which is incorporated in a polymeric material that is used as the electrolyte in your mobile phone device, mobile phone battery. So these battery electrode materials, that actually generates a potential difference between those electrodes, and that potential difference is 3 volt in the case of lithium batteries. Electrolyte also helping in adjusting that potential or varying the potential a little bit. And that's what you have learned in your electrochemistry topics as Nernst equation. Electrolyte concentration can affect the potential of the electrodes. And then the second parameter that we should look at is the Q. We know that now if you take your mobile phone, you are running a lot of programs in that one, lot of apps are running in that, and we are actually looking for higher charge storage batteries. And that's why nowadays the mobile phones are coming with 5,000 or 6,000 mAh battery, but earlier we used 2,000 or 1,500 mAh batteries. But at present, since more current is used in your mobile phones, we have to go for higher charge storage batteries. This charge storage is dependent on the amount of electrode material used, and that amount we can calculate using Faraday's law, and also it is dependent on the exposed surface area. Then the third parameter that we have to look at in an energy storage device is the I, the current. The current is dependent on how fast the reaction is happening, the chemical reaction is happening. and that is guided by the potential difference which is created. And you can get, if the reactant species is highly reactive, then you will get the electrons quickly. And thereby electrons are quickly, if it is moving through the circuit, that means it is more current we are getting. Then this V into Q is actually the energy, V into I, which is the power of the device. Then the fourth parameter we will look at is the specific energy density. That means in a the energy stored per unit mass. And for that, I wish to give an example. You know that the lithium atomic weight is 7, and zinc, the atomic weight is 65.84. And lithium can provide 1 electron per oxidation of 1 lithium atom, and zinc can oxidize and give out 2 electrons. So 1 electron means 1 mole of lithium. If you are taking 1 Faraday of charge, we will get. And in the case of zinc, 65.84 grams of zinc, if it oxidizes, then we will get 2 Faraday of charge, or 33 grams of zinc will provide 1 Faraday of charge. So I can directly say that 7 grams of lithium can provide 1 Faraday of charge, but if I want to store the same amount of charge, I have to make use of 33 grams of zinc. So thereby, per weight, if I calculate per weight, per grams of these materials, when I calculate, the energy stored in lithium is very much high when compared with that in the zinc or other electrode materials. And you know that in the periodic table, we have hydrogen, helium, and then comes lithium, and thereby that is the lowest metal we can take in order to fabricate the batteries. Lowest mass that we can get. Then the another important parameters that we will look at when we are buying a battery is the cost. The battery should be of low cost, then only we can actually afford it. And then availability. Availability in the sense electrode and electrolyte materials availability. If it is not available easily, then the cost will increase. Then in the case of secondary batteries, the cyclability, the cycling stability, that is really important. Then storage stability. The battery we have to store for a long time if it is not, we are not using that one. And for that, we have to consider one important parameter, which is known as the self-discharge. So self-discharge, if it is more, then storage stability will be less. Then safety. Nowadays, we are hearing that the daily, we can hear the lithium batteries are exploded in some places and all. So that is actually the safety concern we have to consider in the case of these energy storage devices. Then scalability. Whatever be the electrolyte combinations that we are making, that should be scalable. That means we have to generate lakhs of numbers of these devices. So it should be scalable nature. And also the design, it should be in a position to design in a particular fashion that can suit for our devices. Say in our watch, we are using the button cell, but we are not using a cylindrical battery in our watch. So the design compatible should be this electrode material and electrolyte materials. Okay. So if we compare the batteries with the capacitors, the capacitor is actually delivering more power, but for a shorter span of time. But batteries which can provide the power for long time. And that is the importance of the batteries which can provide the energy for the power for long time, and the capacitors that delivers the current quickly and but for shorter time. And now we are going to see a bridge between that, and they are known as supercapacitors. So one side we have secondary batteries, which is of high energy, and on the other side, high power supercapacitors. and these high power capacitors. And these supercapacitors has high power as well as energy capabilities. And the researchers are continuing in order to improve these efficiencies, maintaining high power and higher energy power. But at present, we have devices, we have the materials which is having high power as well as high energy, and it needs some more improvement in order to reach the ultimate aim of high power and high energy. Then the supercapacitors, based on its working, are classified mainly into two. One is double layer capacitors, and the other one is pseudo capacitors. And there is a third category, which is known as hybrid capacitors. And in double layer capacitors, the energy is stored electrostatic. The ions, which is absorbing specifically on the electrodes when we are charging it, that decides the charge storage there in double layer capacitors. In pseudo capacitors, charge is stored electrochemically. Similar to that in batteries, there would be some the Faradaic reactions that is happening, and that will store the energy there in pseudo capacitors. And in order to fabricate double layer capacitors, mainly we are using carbonaceous materials. The activated carbon, carbon aerogel, carbon nanotubes, graphene, all these materials are having high surface area, and thereby it can store more ions on it, or which can allow the absorption of more ions on the surface, and thereby it is having it is storing the charge. More charge it can store. And pseudo capacitors, where we have the metal oxides as the electrodes or conducting polymers as the electrodes, they can undergo Faradaic reactions. Then the third category, hybrid capacitors, which is a combination of these two, where the charge is stored both electrostatically and electrochemically. The ionic charge, which is absorbing on the surface, that is also contributing for the charge storage, and the Faradaic reactions that is happening there, that also contribute for the energy storage. So this is somewhat similar to the battery working in hybrid capacitors. Then we have to think of what is meant by this. I said the specific adsorption of ions on the surface. And basically, I would say all the battery reactions are happening on the electrode surface. And whole electrochemistry is the science of studying the electrode surface where electrolyte is in contact. So when an electrode material is dipped in a ionic solution, then the ions which will move towards the electrode, and when we look at the very near to the electrode, the ionic density will be entirely different from the bulk of the solution. And that phenomena is known as electrochemical double layer formation, where on the electrode surface there would be a certain amount of charge which is negative charge, and on the solution side we will have the adsorbed ions that will create a layer of charge which will be positive, and a potential difference will be there between these two layers. And that layer you can actually visualize as a capacitor, because there is a layer of charge in the solution side and a layer of charge in the electrode side. In between that, water or the other solvent can be trapped, and thereby it will act as similar to a parallel plate capacitor, where you have two charged plates, in between that you have a dielectric. And this generates a potential on a electrode surface. And when we are applying a potential to charge the capacitor, these ions will specifically adsorb on the surface, and that will generate the capacitance on the surface. So more ions, if it is sticking on the surface or adsorbing on the surface, we will get more capacitance. And when we are in this double layer, when we are moving towards the bulk of the solution, then this charge accumulation decreases. So the specific adsorption of the ions on the surface when we are applying a potential, and that leads to the capacitance, which is known as the electrostatic formation of capacitance on the surface. Then, depending on the charge stored mechanism, we have, I told you, we have three different kinds of capacitors. And one is the EDLC, double layer capacitor, and the other one is pseudo capacitor, and the third one is hybrid capacitor, which is actually a combination of, which has the reactions, which is a combination of the first two. And in a double layer capacitor, which is known as EDLC, electrochemical double layer capacitors, where you can see here these are electrode materials in which it is depicted there are some pores, and when there is a porous structure there would be higher surface area, and on the higher surface area these ions are going and the arranging, and that forms the double layer, and that creates the charge accumulation on the surface, and that leads to capacitance, and that is known as electrochemical double layer capacitors. Then the second one, where these ions which is adsorbing on the surface or some other species which is present in the electrolyte that can react over the surface of the electrode, that generates more charge on the system, and that is known as pseudo capacitive behavior. And if something is reacting over the surface and electrons are released, then we will call it as Faradaic reaction. So the charge accumulation plus Faradaic reaction is happening in the case of pseudo-capacitive materials. And in the hybrid material, we have both together, which is happening, and we will get battery type behavior for the hybrid capacitors. And you can see when we are moving from EDLC to hybrid capacitor, the Faradaic process happens, and here the Faradaic process is negligible, no Faradaic process, and here there is Faradaic process, and here Faradaic process is one of the main factors. And non-Faradaic process means ionic accumulation, and here you can see in the EDLC, ionic accumulation is the process for storing the charge. Then the thereby the surface area control the capacitance of the device. Then we are using different electrode materials for devising these capacitors, supercapacitors. And there are traditional materials like carbon-based materials, polymers, then metal oxides, metal. Then there comes the new materials for energy storage, which is metal nitrides, metal halides, metal organic frameworks, then polyoxometalates, and then black phosphorus, which is modified with some metals. So all these materials are used in the supercapacitor fabrication, and that can provide very high energy storage, because all these things are prepared in nano dimensions, and that can provide high surface area and high charge storage, as well as the reactions, the electron release will happen quickly, and we will get high power also. So all these materials which is presented here are high surface area materials. Then when we compare, say, the different materials that I have shown in the form of a Ragone plot, I could see that the ruthenium-based materials, material which is coated on multi-walled carbon nanotubes, that you can see which is having high power density, as well as it is having high energy storage capacity. And there are other materials, activated carbon, the n-doped carbon, and all these materials are having charge storage capacity and sometimes lack in power density. And some systems are, they say, cobalt oxide based material that could actually provide high energy density as well as it is having high power density. So only limited number of the materials are compared here, but the research is going in smooth direction not to improve the properties and get more power and energy densities. Then that is one part of the cell system, electrode materials. But we can tune the electrolyte also to get more power stored in the system, power delivery, as well as more energy stored in the device. And for that, there are different parameters to be looked at. One is the ionic size. Then the ion should go into the pores, means the ionic size should match with the pore dimension. Then the energy density of the capacitors can be affected by the concentration of the concentration of the electrolyte that we are using, and also the electrochemical stability of those electrolytes that we are using. Then the power of the device is dependent on the internal resistance of the energy storage device. So the ionic conductivity that will clearly determines the power density of the device, along with the potential window. The potential window, if we are providing a very good potential window, and that will cater more power density from the device. Then the cycling life is dependent on the temperature, electrode-electrolyte interaction, charge storage rate, and all these things are involved in the cycling life of the supercapacitors. And we have in order to decrease the internal resistance, we have the high mobility ions we have to use. And also the electrolyte should be thermally stable, and it should have a good boiling point as well as freezing points to suit in the particular the device in which we are using the capacitors. Then the electrolytes are of different types. As we know, the liquid electrolyte, which is very well common, we know it, this one very well, liquid electrolyte. And there are solid state electrolytes and also redox electrolyte, which is used in supercapacitors in order to deliver more power and store more charge in the system. So there are different liquid electrolytes, water and salt electrolyte, aqueous electrolyte, non-aqueous electrolytes, and all this can be further classified into acid, alkaline, and neutral, then organic electrolytes, ionic liquid electrolytes, and mixture of electrolytes, then dry polymers, gel materials, inorganic materials. All these kind of electrolytes are there that can store charge and then deliver power. Then if you look at the application of these supercapacitors, it can find application in power support. That is, you have a battery and you need a backup power, and there we can make use of supercapacitors, or it can directly provide energy to running the devices, and it can serve in memory backups, and then it can also use as a energy storage device. So in all these applications, we can make use of supercapacitors. And one more thing is, most of these capacitors are working with carbonaceous materials, and that will make environment-friendly technologies. Then other applications, if you look at, we can actually see these devices can be used, these supercapacitors can be used in implantable biomedical devices. And also it can be used in vehicles, as I told you, as a power backup or as a energy storage power device we can use. And the device which is shown here, you can see from the solar energy, the solar panels, the energy is stored in the capacitor, and that can be used for charging portable devices. And similar way, if you have an electric vehicle and if you have a parking area where on the roof there is solar panels, and the energy can be stored in a supercapacitor, and that can be used for quick charging of the electric vehicles. So in all these area, the supercapacitors can come into and play a major role. Then I would like to bring another area in where we can make use of supercapacitors, which is known as wearable devices. And what wearable device? I don't think there is no need of an introduction for that. Almost all are using smartwatches now. So in the smartwatch, you can see there would be several sensors, as well as it will work as a watch function, the time function it will show. And there are other functionalities incorporated. And in order to run these devices, we need power. And in order to sense different parameters like the pulse oxygen, the BP or the other health parameters, we have sensors there. And in order to run those sensors, we need power. And the supercapacitors can be used to power those devices. And not only smartwatch, we can have smart glasses, smart bracelets, smart fingers, and all these things can be incorporated with the different sensors, and thereby you can even monitor your health parameters. Because nowadays, all are so conscious about the health status, and thereby these devices can provide this device, the energy storage device, supercapacitors, that can act as a very good energy storage device for running all these devices. So if you want to use such kind of a supercapacitor in the wearable devices, one of the important parameters that we should look at is the supercapacitor that we are using. If you are wearing a smartwatch and you are incorporating this supercapacitor, suppose in the strap, then the strap is deforming when we are actually tying it on our hand. So that time, this supercapacitor performance should not get affected. So one of the important parameters that we should look at when we are thinking of wearable energy storage, the supercapacitor should be flexible. That means the mechanical deformations or stress should not affect the working of the supercapacitor. And thereby, people have designed different supercapacitors. One type is known as sandwich kind of supercapacitors, where the electrode material is kept, and electrode materials are there on bottom and top. In between that, the separator with electrolyte is incorporated. And it can be incorporated, we can incorporate gel electrolytes in the planar form, or it can be wire type supercapacitors, or it can be cable type supercapacitor. That is, the electrode materials and the electrolyte is separated. You can think as two separate cables, and in between that you have the electrolyte material incorporated along with the separator. And that kind of devices are there, which is known as cable type supercapacitors. Okay, and different forms we can actually make these capacitors. And electrode material for these devices, as I told you, the activated carbon, carbon nanotubes, graphene, metal oxides, conducting polymers, and MXenes, which is actually metal halides, and those kind of electrode materials. The research is happening in a faster way in order to improve the efficiency and bring supercapacitor as the best energy storage device. Because from an energy storage device, what I am expecting is I should store more charge and I should get more power outcome. And flexible supercapacitors also, we are expecting such kind of electrode materials. And no doubt, electrolyte area also, lot of research is happening. And one fabrication part, just I want to show you how we can fabricate such kind of a device. So you can see here the graphene hydrogel, which is coated on a gold plate, or you can use a copper plate on which you are coating. This taken from a research article, and they have used the gold plate on which they coated gold film, and on which they coated graphene hydrogel, which is the electrode material. Instead of gold, you can use copper material. And then after that, you have to incorporate the electrolyte on top in the form of a polymer electrolyte. Then keep another plate of this graphene hydrogel on the top, and then you can press it, and then that will act as a, you can see one electrode here, another electrode here, in between that sandwiched electrolyte, and that will act as a supercapacitor. Because of the high high surface area of graphene hydrogel, it can store very high amount of charge, and it can be made into the flexible form. You can see here they are bending the supercapacitor, and the efficiency is not affected upon that bending cycles. And another one is the printed supercapacitors. You can screen print, or you can print these inks of the capacitor materials on plastic materials, and you can use that one as a flexible capacitor. And another one, the important thing that you can see here, you can make wire kind of supercapacitors, where inside there is one particular material, and around that you have another electrolyte material, and which can be a polymer, and on top of that one another electrode material you can make, and you can make that one as a capacitor, wire kind of capacitor. So this kind of very good, interesting research is happening in the area of supercapacitor. And in the Coimbatore campus where we are working, what we do in our Biosensor Research Lab is we are making different high surface area nanomaterials. And basically, we earlier focused on the sensing application, biosensing applications, and now we are focusing on the energy storage. And thereby, we synthesized a lot of high surface area materials, and we synthesized high surface area materials, graphene modified with several nanomaterials, and we used that one for flexible supercapacitor, which is screen printed supercapacitor fabrication. And what we do is we will synthesize, and we will mix that one as a conducting, we will make that one as a conducting ink, and that will coat on plastic plates, PET substrate, polyethylene terephthalate substrate, and the electrolyte in the form of a gel, PVA KOH gel, we used to incorporate in that, and we could use that one as an energy storage device, and we could establish the working of some calculators, the low power devices, at present, low power devices with these supercapacitors. And it could run for 15 to 20 minutes. The device could power the, say, this small, the supercapacitor, which is printed, that can work for 20 minutes energy delivery or power delivery. Then what our aim is, we want to integrate this capacitor along with the sensor that we are developing, and we have to make it as a non-invasive device to monitor health parameters like glucose, urea, ammonia. It's kind of the health parameters from, say, the electrolyte sweat. Sweat can act as the electrolyte, and that contains all these kind of biomolecules that we can sense. That's what our the research work which is going on. And in a nutshell, I can represent whatever that we discussed so far. The capacitors are of three different types of capacitors that we have seen. One is EDLC. We will start from the bottom. EDLC, pseudo-capacitors, Faraday pseudo-capacitants, that is the hybrid capacitors. Then cell designs, we have symmetric and asymmetric cell designs. Then applications, we can use that one in different devices. And in order to fabricate such kind of devices, we have different materials like carbon, metal oxides, metal nitrates, such kind of materials. And also we have electrolytes which is either the aqueous, non-aqueous, gel electrolytes, polymer electrolytes, all these kind of electrolytes we can use. Then the speciality of supercapacitors so far we have seen is they are having high energy density and high power density. And also it has long cycling life. Theoretically, there is no need of replacement for this particular device because the device will run for n number of times. Charge discharging we can make n number of times. Then now at present there is it is having high cost, but with the development of this kind of new materials, we can actually bring down the cost. And design can be easily tuned. Also, the materials used for this fabrication are environment friendly. Then, what is the future of these devices? As I told you, there are a lot of research is happening on the new electrode materials design, and also in the electrolytes part. Also, we are lot of people are working on the design aspects of the supercapacitor devices, and also the cost effective fabrication methods. So when all these things are joined, then we can have the capacitors or the energy storage devices for the electronic devices, because at present we know that there is a rapid boom in the development of electronic devices and also electric vehicles, where we can make use of the supercapacitor technology as the energy storage device. Also, as I told you, the non-invasive medical devices or in invasive medical devices, we can make use of supercapacitors as energy storage device. So with this, I wish to thank all of you for listening to me. And if you have any queries, please put it in the chat box. I can answer. Thank you.
That was a wonderful section from Suneesh sir. Sir, thank you for spreading the wisdom of knowledge about superconductors. Thank you all the participants for participating in this session. See you on the next Saturday. Thank you, sir.
Okay. Thank you. Thank you.